Now, what happens when carbon dioxide is emitted into the atmosphere? The basic point is a lot of it stays there. Imagine your bathtub, and it's got a little hole for the water to go down, and suppose that it's partly plugged, so the water's not going down the drain as fast as it could. And suppose that the water's coming into the tub at full force. The tub would be continuing to rise even though some of it would be going down the drain. And that's like carbon dioxide. Some of the CO2 in the atmosphere actually ends up in the soils or ends up dissolved in the ocean. But if we keep pumping CO2 into the atmosphere so fast, even though some of the CO2 is being taken up in what are called natural sinks by nature on the land or in the oceans, the amount that's going into the atmosphere is so big, so fast, that the amount total, that's like the level of your bathtub, that just keeps rising, 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 because the water's coming in faster than it's going out. Well, so too is the CO2 going into the air faster than it is being removed into the soils or the trees or the ocean. Starting more than 50 years ago, a wonderful, wonderful scientist had a really smart idea. Mr. Keeling said, I'm going to put a monitor of CO2 up on the top of a mountain in Hawaii, far from all the city congestion and direct effects, and I'm going to measure the Earth's carbon dioxide concentrations. And he knew something also very clever and very smart, which is that it doesn't really where you measure, it doesn't matter where you measure the CO2. The CO2 mixes in the atmosphere homogeneously. It's a uniform mixing over a period of about 30 days. Doesn't matter where it goes up, the whole world ends up with that blanket of CO2 around it. So Mr. Keeling started measurements back in 1960, and he had a little sawtooth going up and down, because CO2 is released into the air when the leaves fall in the fall, and the carbon in the leaves goes back into the air, and then the CO2 comes out of the atmosphere back into the plants as they grow in the springtime. So up and down, sometimes called the lungs of the planet. You see the breathing there, but more than the up and down effect, you see an upward sloping curve. The concentration of CO2 in the atmosphere has been rising rapidly, dangerously. And since the warming effect of carbon dioxide depends on the overall concentration of carbon dioxide in the atmosphere, that upward sloping curve, meaning more carbon dioxide in the atmosphere, means more human-made warming. How do we measure the concentration of CO2 in the atmosphere? We measure it as molecules of carbon dioxide per million molecules in the atmosphere as a whole, including all the other parts of the atmosphere like N2 and O2 and other atmospheric gases. So it turns out that before industrialization, there were 280 carbon dioxide molecules on average for every million molecules in the atmosphere. 280 ppm, parts per million. Then we started burning fossil fuels, coal, oil, and gas. Burn them, CO2 up. Chop down the forest, CO2 released into the air. Mr. Keeling measures the curve. Back in 1960, when he started the measurements, it was about 315 parts per million, up from the 280 pre-industrial level, but still pretty close to it. Then look at that rise of carbon dioxide concentration. We have reached more than 400 parts per million CO2 in the atmosphere in a very short period of time, in a little bit less than half a century. That's what's leading to this dramatic human-made warming. Now we come to the carbon budget, because we have to ask the question, okay, we have raised the carbon dioxide concentration from 280 parts per million in the pre-industrial level to more than 400 parts per million because of chopping down the trees and burning fossil fuels. We've raised the temperature to warmer than the pre-industrial level. How much more carbon dioxide dare we emit into the atmosphere before we have violated every measure of safety, before we have trespassed on that critical planetary boundary. Well, scientists have said we have a carbon budget. We have a total amount that we can burn and still have a chance of staying below a certain limit. And here's the problem. We're basically bursting the budget. We're going to go broke the way we're going right now. What the scientists say is that if you measure all the way back to the beginning of the industrial age, back in the 18th century, and then go all the way till now, and all the way forward to the limits, we could emit 3,600 billion tons of CO2 and still probably stay below 2 degrees Celsius. Then they say, yes, but up until 2015, starting all the way back in the 18th century till now, we've already emitted about 2,000 billion tons. So we're running out. Then, if we're left with 1,600 tons of carbon dioxide budget that could be emitted and still probably stay below 2 degrees Celsius, we have to take into account that there are other greenhouse gases. It's not just CO2. There's methane, there's nitrous oxide, there's hydrofluorocarbons, and so forth. That's already eating up part of our carbon budget as well because they're warming the planet. That means there's less space for the carbon emissions. Take away another 750 billion tons that we can't emit from CO2 because of these other greenhouse gases, and we have a remaining budget of about 850 billion tons of CO2 left that gives us a likely chance of staying below 2 degrees C. Now, there's lots of words in that sentence that I just said. What do I mean by likely? The scientists mean at least a 2/3 probability of remaining below 2 degrees C. So to put it more scientifically, according to the carbon budget, if humanity limits its future carbon dioxide emissions to 850 billion tons in the years ahead, we have a 2/3 or 66% probability of staying below 2 degrees. That's not very good, by the way, for two reasons. One is we promise to stay well below 2 degrees, not to reach 2 degrees. 2 degrees is incredibly dangerous. So we said we've got to stay well below 2 degrees. And 850 billion tons isn't going to stay well below 2 degrees. We'd have to have an even smaller carbon budget for that. And it only gives us 2/3 chance of doing it because 1/3 chance we'd be above 2 degrees C. So when I say that there are 850 billion tons of carbon dioxide in the future that could be emitted, that's not a safe 850 billion tons. That's a risky 850 billion tons because it could take us well above safe limits of warming. But here is the point. Please pay attention. We are now emitting about 36 billion tons of carbon dioxide every year at the current rate. Do the arithmetic. Divide 850 remaining tons in that carbon budget for a likely 2 degrees C, divided by 36 billion tons per year. Oh, my word, that's about 24 years left at the current rate. But the world's not at the current rate. The world is a growing economy, so even the rate of emissions is going up. What's the conclusion? The conclusion's pretty frightening. It says we're basically out of time, which is we cannot even continue the current level of emissions for another generation and be safe. We have to turn the curve on emissions to stay within the carbon budget by getting those carbon dioxide emissions down sharply, and we need to get them down fast. Many scientists, many that I admire, say we're already past the point of safety. Don't even talk about further emissions. We have to get down to zero very, very fast. Probably if we're at more than 400 parts per million and rising by 2 to 3 parts per million every year right now. We have to stabilize at maybe 420 parts per million and then start getting the carbon dioxide out of the air. If we go up to 450 parts per million, probably we don't have better than a 50% chance of 2 degrees, and 2 degrees is too high. If we go above 450 parts per million, the dangers are completely profound. My colleague, Dr. James Hansen, one of the world's greatest climate scientists, says the only safety is to get us back to 350 parts per million by capturing that CO2 already in the air and getting it back into the soils and into forests that are allowed to grow again, and to stop new emissions, or to capture the CO2 in the atmosphere through chemical processes and put that CO2 into safe geologic storage. I'll come to that. We have a number of technology options, but the basic idea of the carbon budget is we are running out of time. We have to understand how dramatically we need to stop the rise of emissions, start the decline of emissions, and then get emissions down to zero within a short period of time. That's my topic of the next chapter.